Alright, so I make a start. It's now 1 o'clock UK time, so welcome to some data analysis. Now this is a live stream. Hopefully the quality is acceptable. If not, I think I will also happily do a recording on it. It all depends a bit on Wi-Fi quality, and sadly our Wi-Fi settings aren't the strongest in our case. Now what I want to do in this live session is I want to explore a data set, and I want to take maybe around 35-40 minutes to go into some descriptive analysis and then move into a regression analysis. So that's the purpose of it. After this streaming, there will be a recording available, but I think I might need to do some further editing. If I find the quality not good enough, I might anyway record this one more time properly to ensure that the quality is up to standard. You will find all the links, all the data sets, the codes, the slides, everything on GitHub. The link to my GitHub is on the YouTube page, and today I will focus on data science using Stata. So we will use Stata to explore our data set. So if you haven't used Stata before, I strongly recommend have a look at this material. You also find in here the slides. So in here we have the slides. I think there are more than 140 slides focused on data science using Stata. In particular, I would recommend lecture 3 on regression analysis. So this covers the main aspects of today's session. I won't go into post-estimation analysis, so I would cover this in a separate session. So I focus very much on exploring data, transforming data, and understanding outliers and understanding potential issues. And then I move into analyzing data using regression analysis. So that's the main purpose. Then I will talk a bit more about aspects of model specifications. So actually I move a little bit further down even more into issues around model specification. So here we are, so that's lecture 7. So that's the main aim for today. You have material already here in live 1. So these are the live recordings, and in this folder you have the data set and you also have the do file, which we will now discuss step by step. Good, so I hope you enjoy that. You can always leave some comments. I won't be necessarily able to go live into them because I will be quite busy in Start and I would move applications otherwise. But I will try to get back to you after this session if you have any comments about it. And I will also make the recording available. Good, let's get into it. So the first thing to do is to look at our data. I put it all into a folder. The original data was stored in Excel, so that's here the original data set. I'll just open this, it might take a few seconds. The data is available for free. It's provided by the World Bank. So these are data from World Development Indicators. So they're quite easily obtainable over quite an extended period of time. I included all the countries available in terms of data. In this data set in particular we have annual GDP growth rates, so this is economic growth rates. You nicely see here the impact of the global financial crisis in the case of the UK. And we have inflation. Again, it's an annual measure, so inflation rates. We have the lending interest rate. Now this is the interest rate you would charge on loans. then we have the official exchange rate and we have the growth rate of money. So this is basically the supply of money. This is the M1 actually. So this is the amount of money in the economy. And of course you had lots of money creation in this period because of all the interventions of central banks. So I won't go into the economics of this discussion, so I won't cover this. I will focus entirely on analyzing the data. So that's the original data set. I won't cover how to move from the data into Stata. Again, I'm happy to do this in a separate session if this is what you would prefer. So let me now move into Stata. So I opened up Stata, and actually what I might do is I might just remove everything I have done before, and also I clear my data set for a minute just for you to see actually how you get there. I opened up a do file. I just now use a new do file where we start our analysis. To do some comments, you can always use the asterisks, and you might call this here macro analysis, whatever you want to call it. So we make it a little bit looking nicer. And I start zooming this a bit so it's easier to see. The first thing you have to do is you have to change directory into the folder where you keep your data set. Yeah, let me just now anyway save this do file. I just call this attempt. So that's our do file. And in here I do a change directory, and when I want to navigate into where you store the data. If you don't know your directory, the easiest thing to do is when you are in Stata, you just open it directly. Yes, I'm working here on a Stata 16 version. You can use any version of Stata. In fact, for most of my recordings I use Stata 11 or Stata 13. It doesn't make a difference. Yeah, so all these things work on older versions of Stata. So let me just open here the data set. So that's our macroeconomic data set, and now it gives you of course also the path. We can just copy paste all of that if you want. Copy paste that in here. We anyway have to use again in a minute to open the data set, so we just copy paste that. I remove the path. You can do it all in one go, but I quite like to separate these because I want to separate the path, changing into the path and actually opening the data. The use command will open your data. If you already have some data in memory, it would not allow you to do this. Hence, I add here the clear option. Yeah, just specify clear. And I run this one more time. In here, I should be now able to see my data set. Yeah, so that's always the first step. To explore the data, have a look at the structure, try to understand the structure before you move forward. Again, you're more than free to explore the data yourself. The data is from the World Bank, so it's freely available. There's no copyright issue or whatsoever. You can use the data and you can also use it for your own analysis. I just now browse the data, so I just type in BR for browsing. By the way, I use usually commands because I'm used to Stata 8 when it came out, so all the fancy menus did not exist, so I'm very used to using the commands, so I'm just sticking to that. So in here we can see the data structure. So you have different countries over time. So that's the structure. One country over a certain period, the next country over a certain period. You certainly have some missing data indicated with the dot, so that's an indication for missing in Stata. Sometimes you wonder whether the data quality is really convincing. So in here, that's all 0, which might or might not be the case. It's a bit suspicious. But in terms of data structure, what you certainly have is you have panel data. Yeah? So you have a cross-sectional dimension, the different countries, and then you have a time dimension, the years. So you have a panel data set. And then you have several variables, including the GDP growth rate, inflation and lending rate, the exchange rates, and then the money supply. Now, this then, because it's the exchange rate, most likely that is basically indicating that it of course always depends what's your reference currency. I suspect it's the US dollar, and if you have a fixed exchange rate regime, it does not change, so then it might make sense, yeah, in terms of having a 0 here. So that's the structure of our data set. So the first thing I would like to do is I like to add some labels to my data. Because I almost promise you, when you work on a project, whether it's a dissertation project or even worse, a PhD thesis, after maybe years, doing this project, you might find it exceptionally difficult to remember what the different symbols mean. So I strongly advise you, based on my own experience, to use labels for all these variables. So that's the first thing I would like to add. Good, so in here what I would now suggest is let's add some labels. Now, to add labels in Stata, we use the label var command. So in the latest version of Stata, you get now even some help with commands. So of course all of this didn't exist when I started. It's pretty cool actually. What I would do is I would just go back to Excel and just copy these names, yeah, to make life easy. Let me just copy paste that. So these are the names, and then we can just move it where we want to have it. So the first thing would be we have G for the growth rate. So this is GDP growth rate. I put this into quotation marks, double quotation marks, to make it, in this case, a string. So this would be our label. Let me just anyway copy paste the command, and then we just add the different symbols. If I'm not mistaken, inflation is INF, and again here I do the double quotation marks, and in here we have the lending rate. I believe it's R, I might be wrong, we will figure it out in a minute. The exchange rate is E, and again I use the double quotation marks, and then we have the money growth, which I believe is M. So that should do it. So after you have done the labels, I would just do a describe command. Yeah? So des is for describe. It will just simply show us the labels and check whether it's working. So I now execute my do file and go back into my Stata output. And as you can see, we have now labels introduced. And I think that is definitely very useful. So even after a few years, when you go back into the data set, you now remember actually what it is. I don't think you need labels for year and country and code and so on. I think you should be okay with that. I want to mention one thing, but I won't go into the details here. When you look into a country would be a string. So in terms of color coding in Stata, red color would refer to a string. Code is a country code. It's an acronym, it's a shortcut. And this already has been what is called decoded. So this has been converted from a string actually into something numeric. It doesn't look numeric, but actually it is. So now when you want to tell Stata that you work in panel data, you can use code as your cross-sectional dimension. This is just something to have in mind, because Stata doesn't like to use strings for identifying a cross-sectional dimension. It always needs a variable that is actually functioning like a numeric. Yeah, so that's something you have to get used to. It's a bit annoying, but it is what it is. Good. Now the next thing I would like to do is to now declare a panel data set, because we know it's panel data, but Stata doesn't know it. So what we do now is we specify the panel data. You can use the tset command, and we start with code, this is the cross section, and then we continue with year, this is the time dimension. And we just run this all one more time, and now we have specified our panel data set. In this case, it's a so-called strongly balanced panel data set, which means we have the same number of cross-sectional units for all these time periods. So every country has, in principle, data from 2004 to 2012. Of course, we already have in mind there are sometimes missing data. So it doesn't mean that there is no missing data. There is missing data. Good. The next thing I always like to do is to go into some basic descriptives. Yeah, also when you work on a project, whether it's now a dissertation project, PhD thesis or whatever, it's nice to have a table for descriptives. Yeah, so a table for some descriptive analysis, for descriptive statistics. Let me just do this. My typing isn't great, yeah, so I'm certainly making lots of spelling mistakes, but you know, that's okay. I'm into data, so data is important. Spelling isn't too much. Good, so what I would do is I would use a tab stat for that. So that's quite nice because you can modify the output. And I would put in our variables. So we have our growth rate, we have inflation, we have our lending rate, exchange rate, and your money supply, growth rate. I put a comma here because now we can modify what we would like to see. I use stats for statistics. And in the brackets, I now specify what kind of stats I would like to have. For instance, n is number of observations, definitely useful. We have the mean, we have the standard deviation, and then it depends what you want to show. So many people show a minimum value and a maximum value. I very often actually show percentiles. So I might show the bottom 25% percentile, followed by the median, and followed by the top 25%. So this gives you a good range of your observations. If you put in the minimum and maximum, of course, in a large data set, you will get only the outliers. You will get a few very extreme observations, like, you know, inflation rates in Argentina, for instance, which are kind of crazy. Good, and then we can do some further formatting. We can, for instance, force a format that might look nice in a table. So to do a format, I use percentage sign. I have maybe up to 9 figures. I use 2 decimals, and I do a fixed format. So that tends to look quite nice. If I just now mark this and run it one more time, we now have quite a useful table. So we have observations, up to 2000 observations. We have our mean, standard deviation, and we have our percentiles. So that's actually like a box plot. Yeah, so that gives you an idea about the range of your variables. Now, quite often when you compare this to publications, in publications it's much more common to have your variables in rows and have these statistics actually in the different columns. Yeah, so it's a matter of taste. If you want to switch it over, what you can do is you can just add another option here. C stands for column and S stands for statistic. So this would switch it over. And it would look then maybe a bit more appealing for a journal publication. Now, there are many ways to export your tables. I have done also a video on exporting tables, but the easiest thing to do, which is honestly perfectly fine, is to simply copy paste that. So if you mark it and you do a right click and you copy table as HTML, it will more or less preserve the structure. You go into Excel, we just now start a new one, and you just copy paste that in. Yeah, so you can copy paste that in, and it should be reasonably fine. You can also change, of course, the formatting, so we can ignore the original format. And in here you need to always do a little bit of edits, but it's kind of easy. You can always modify things a little bit. You can also, you know, add a bit more structure into it. For instance, in here you might like to do a border, you know, something like this. Yeah? So you can modify that, and of course once it is in Excel, it's very easy to export into Word if you want to use Word, or if you want to use PowerPoint, it's quite easy to handle. So now we have our descriptive analysis done. Our main table is also done. And it looks reasonably fine. Again, you can do some further formatting. Again, another right-click format cell, and you might, for instance, specify here numbers with 2 decimals. You can, you know, tidy this up a little bit. Yeah. So that's looking quite acceptable. That's the easiest way of doing it. Quite often, I think that's fine. If you only have a handful of tables, I wouldn't really bother. Of course, if you want to rerun your analysis and you want to you know, update or keep updating your tables, in this case it would make sense to actually do some proper coding and actually you know, check out and code these tables into Stata and basically automate the updating process. But this is more advanced. I'm happy to do another you know, session on that. But I would say for most applications this is perfectly acceptable. Good. So now we have our main descriptive statistics. And of course now what do we get out of it? Yeah. So what more do we need to do? I would always suggest, if we in particular want to go later into some regression analysis, to do some correlations first, to do a correlation matrix. Yeah? I did another video on multi-collinearity. Yeah? So this is an issue in regression analysis. If your variables are highly correlated, it becomes very hard to separate the effects in a regression analysis. So it's useful to run a correlation matrix, which we just have done here, and just check is there any significant issue. Now the question is, of course, what is a significant issue? So usually the literature would argue anything in absolute value in excess of 0.85 would signal a high level of correlation, which most likely would cause problems in regression analysis. Yeah. So looking at that, it doesn't look too problematic. Of course, you will have some correlations. It's to be expected because we have here macroeconomic variables that tend to be correlated. So it's not a big surprise, but it does not seem to be highly problematic at this point. Good. The next thing I would now do is I would look into these distributions a bit more carefully. Before I do this, let me just quickly check whether there are any comments. Yeah, so now this is, of course, it's recorded. Yeah, so it will be available later to watch. E means exchange rate. Yeah, so that is the exchange rate, the changes in exchange rate to be precise. Yeah. So again, we do some recording as well. So if fingers crossed, if the quality is okay, I would just keep it, make it available. I might do some further mods, I guess, in terms of you know, some further edits in this case. Yeah, let me just minimize that. Good. Okay, let me just minimize that, because otherwise you always see my screen. I'm switching between applications here. Okay, so good. So this is my correlation. not a problem at first. So the next thing I would quite like to do is I want to really go into the distributions. Yeah, so because that is quite important before you do any regression analysis. Have a look at distributions. There are many ways to visualize distributions. I'm quite sure you came across a histogram, for instance. So a histogram is quite useful to see the distribution. I do a different version of it, which is called kernel density. So it's simply K density, and then the name of your variable. The first thing I want to look at is I want to look at my GDP growth rate and just see how that looks like. And let's see, so that's my GDP growth rate. It's looking all right, yeah. So what you would like to see is that your distribution it looks more or less normal. It will never be 100% normal, to be honest, but it should look kind of symmetric. Otherwise, you might consider transformations. And I did another video on transformations and when to use them. And also to be careful sometimes with transformations. So that looks okay, that is not a problem. What you can also do is you can use a summarize command with detail as the option. So this gives you also an overview of your variable. So this is more detail, it goes deeper in. So here what you see is now you see the different percentiles. And you see again your mean and your median and all the core statistics. Now what you should look for is the following. Have a look and compare your mean and your median. You see in this case they are very, very similar. Yeah? So this gives you the idea that the distribution is more or less symmetric. Yeah? So it's more or less symmetric. A similar finding you get from the skewness. So the skewness, if it's slightly positive, it means that it's more likely that you have slightly more large positive values. But here the skewness is quite close to 0, which again indicates it's quite symmetric. So that's good. The kurtosis is relatively large. Yeah? So this is actually also what you see on stock markets a lot when you look at stock returns. This is an indication of what you call fat tails. So it's more likely you have extreme outcomes, so very negative or very positive. But otherwise, this is not looking too bad. Yeah? The other variable of interest is inflation. Yeah? So if we do the same now for inflation, things look a little bit different. So again, I'm lazy, I just copy paste that, and I throw in here inflation. And just have another look at inflation. Now inflation is a different animal, and you see it's quite extreme. You have a few very large observations that skew your density quite a bit. Yeah? So that is a bit of an issue. And also when you now use the summarize detail, you see as well that when you compare your mean and your median, that the mean is much larger than your median. Now this means that there are a few very large, very positive variables that simply skew your distribution. Yeah? And you see that also here when you look at these values, there are some very, very large values in inflation rates. Yeah? So these are cases like Argentina, where you have massive runaway inflation. The kurtosis again is very large, yeah? So quite extreme, again indicating extreme observations. And you see a very large positive skewness. So positive skewness means it's much more likely to have very large positive values in inflation than very small negative values. Yeah? Anyway, deflation isn't very common. So that's important to have in mind, and is definitely useful. So what happens a lot in the literature now is to actually do some transformations. Yeah? So transformation means you take your original variable like inflation, and then you modify it, you calculate a different variable. In inflation rate measurements, the most common way to do is to use basically so-called log return modifications. So I call this the log inflation. So I use a generate command to generate a new variable. I call this the log underscore inflation, and it's simply the natural logarithm, so ln, in brackets 1 plus the original inflation rate. So it's no longer the original inflation, it's a modified version of it. And I show you now an academic paper, it's by Gilman. I will put these links to the papers, in fact, on GitHub, so you can have a look yourself. So that's it's a very good paper. I won't go into the details because it's not necessarily massively relevant for analyzing data. And it would go a bit more advanced into macroeconomics. Yeah? But basically what this paper does is it looks at this relationship between GDP growth rates and inflation. And it also talks about measures of inflation, and in particular nonlinear effects between inflation and growth. And in fact, in our analysis, we want to explore this a bit further. Yeah, so that would be also a nice paper to have as a starting point for your own, analysis. So basically what this paper argues is that inflation and growth has a nonlinear relationship. Yeah, so that's the argument. Whether we find it in our data, we have to see. I'm not too sure about this. But in here it talks about the measures of inflation. And in one of these, I think it's in here exactly. So here you see the modification. Yeah, so this is actually how it's modified. So taking the log, actually this is the ln, of 1 plus the inflation rate. So this is what we have done. Yeah, so we modified our inflation to compensate for the fact that sometimes inflation rates can be very, very large, so it has a positive skew. Now after the transformation, if you go back into your k-density, look at the distribution again, you see actually the impact. So if we run now everything one more time, I just run it all one more time, you see that all of a sudden it looks much more symmetric. Yeah? So after the transformation, it almost looks perfect. Yeah? It's not quite normal, but it looks an awful lot better. You can certainly argue that. So in most empirical papers, people would use the log inflation measure in regression analysis. So that's important to note. Now again, before I do regressions, the next thing I always do is I look at some scatter plots. Yeah? That's another thing I would strongly recommend, because many effects you don't see easily in a regression model. In particular, if you have a strong nonlinear pattern, it's better to spot this pattern in a scatter plot. Okay, so what we do is I use here scatter, and I want to relate my growth rate and inflation. You will see in a minute that this will be a little bit tricky, let me just run this and let's have a little look. So what you of course observe is you have outliers. So these are the outliers we already discussed before, a few very, very large inflation rates. Yeah? So again, a scatter plot can be useful to spot outliers. Yeah? So the other thing you can now do is you can simply save this figure. You can just simply do a copy paste and you save it, and you can simply put this into Word, whatever you want to use for your report writing. But certainly there are issues of outliers. So the other thing we already have done is we use now this log transformed value. So we can do now the log version of it, do it one more time. And you see it's much better. It's an awful lot better. You will still have a few places where there are some outliers, but looking at this just as a first impression, it's not obvious that there is any relationship. So it's neither positive nor negative. It looks kind of quite random. Yeah. So that's the first impression. Of course, it can be deceptive because we only look here at these two variables. We don't add any further controls, anything like that. But it gives me the first indication that honestly, it looks as if there is no strong relationship here. That would be my first impression. Good. So now the next big step. So after going through labeling, going into descriptives, correlation, distributions, the next step is now indeed to do some regression models. Yeah. So this is actually now where the fun really starts. So I now start doing some regression analysis. Again, it's very, very easy to do this in Stata. We can just do a rec command. I want to explain my growth rate using inflation. In fact, I want to really start with this very, very simple model. Just want to run this. And also what I want to do is I want to actually store the estimation output. So you can do here an estimates store, and you can name it. I name it A. So the good thing about storing your estimation output is you can use it later if you want to do another summary table, for instance. Yeah. So now let me just run this. Actually, in fact, to be honest, I want to do the log version here. That might be better. Let me just run that and look at the output. Okay, so this is standard regression analysis. I will talk now about this output and how to interpret the output. First, you have 1,796 observations. Now, this is a good number. This is quite a solid number. Then you see here the F-test. Now, the F-test is a test of a joint hypothesis that all the coefficients in your model are jointly equal to 0. Now, in our case, we only have two coefficients. We have a constant term and we have our slope coefficient related to our log inflation measure. Clearly, looking at the p-value of your F-test, you can reject this null hypothesis with certainty, honestly. Yeah? So the p-value is certainly below 0.05, which means with 95% level of confidence, you can reject the null that all the coefficients in the model are jointly equal to 0. Yeah, so this is a very strong indication that the model as a whole has some predictive power. Yeah, some predictive power. It's not perfect, but I think it's reasonable. Now the adjusted R-squared gives you the percentage of your observed variability of your dependent variable explained by the model. So put differently, this model would explain 5% of the observed variability of GDP growth rates. Now this is not much, okay, so only 5%, but also have in mind we only add inflation here, we don't do anything else. Yeah? For only one measure, I would say this is quite decent. It's not bad, we don't do anything else. You see also, looking at this coefficient, that the p-value again is below 0.05, which means with 95% level of confidence, you can reject the null hypothesis that the coefficient is equal to 0. Okay? Now this means that there is a positive, coefficient is positive, and significant effect of inflation on GDP growth rate. Now this is not uncommon, it has been documented in the literature, but quite often people argue there is an upper limit at what point it becomes less of something positive. Yeah? So in particular if you go into hyperinflation. What you also see is you see the t-value. Now the t-value is just an additional thing you could report. If the t-value in absolute value is larger than 1.96, it again means that with 95% level of confidence you can reject the null hypothesis that this coefficient is equal to 0. Now here it's clearly, of course, in line with the p-value indicating significance. The t-value is derived from taking the coefficient and dividing it by the standard error. This gives you the t-value. Another way of looking at the same problem is to look at the confidence interval. Yeah, so this is the confidence interval of your estimated coefficient. Yeah, so the coefficient here is just in the middle of this interval. So how to construct this? You take your coefficient plus minus 1.96 times the standard error. This will give you the confidence interval. And as you can see, the confidence interval is all positive, which means 0 is not part of your confidence interval, which means you can again reject the null hypothesis that the coefficient is equal to 0. So you can do hypothesis testing either using the p-values or t-values or the confidence interval. It's also called the duality principle. Yeah? So you can do interval-based hypothesis testing. So this gives you a quick summary of the main things to look for in a regression model. I will just stop here and just see if there are any comments. Let me just quickly move in here. I will add the name of the papers as well, so don't worry about it. I will put the name into the GitHub. Let me just see anyway if I can just copy paste that. If I can, I just put it in here. So it's inflation and growth explaining a negative effect. So they argue there's a negative effect. In fact, we see that, here we go. We see that it's actually maybe a positive effect, so we are not quite consistent here, so that's a little bit funny, yeah. So, okay. Okay, this is sometimes, this is the beauty of doing, empirical modeling, because you never know, yeah. Very often you might contradict some papers, yeah, so, but, that's life. It is what it is. Good. The next thing I want to do is, so this would be maybe a nice starting point. So very often I start simple. Yeah, I just take the variables I'm mostly interested in and put them into a regression model and just see, does it make sense? Yeah. So here we get now a first impression that there is most likely a positive, most likely a significant impact of inflation on GDP growth. Yeah. Okay, what I would do next is I would add now controls. So we add control variables because, and now call this B, because it's quite likely that other factors, of course, also affect now growth rates. Yeah. So what I do now is we just use all the remaining variables, in particular interest rates, where interest rates will have an impact. Exchange rates, they have an impact for sure, and also the money supply, which most likely also has an impact. Of course, these variables are not independent, so there is a degree of correlation between them, but we looked at the correlation matrix, it didn't look too problematic. So most likely we should not have an issue with multicollinearity in this case. Yeah? So let me just run this and see what happens. So do we change our main insights? So now, first of all, what you notice is the f-test is still indicating the model has explanatory power. So the p-value again is very clearly below 0.05. No doubt about this. So again, you can argue that the model as a whole has a decent amount of explanatory power. So that's good. The adjusted R-squared massively improves. Yeah, so here we can explain now 21% and a half of GDP growth rates. Now this is actually quite a lot. So that is quite decent, definitely decent. So there is no doubt that there is a serious amount of predictive power covered in our variables. Again, the inflation remains significant. Yeah? So you see the p-value remains below 0.05. The coefficient is still significant. However, you see that the magnitude of impact goes down. Yeah? So it's a bit diminished in terms of impact, because now other factors, of course, also matter. Yeah? The interest rate doesn't seem to matter. Yeah? It's not significant. So most likely these effects are captured in the monetary component here. So money supply certainly matters, is a big driver of growth rate. Also currency changes matter. So usually if your currency gets stronger, it's not a good thing. Yeah? So having a negative impact here usually makes sense, because a weaker currency, again, if it's not too extreme, so a little bit a weaker currency helps you in terms of export. So some countries which are more export driven, they do actually benefit from weaker exchange rates. So Japan is a good example. The Japanese central bank quite likes to keep the yen quite weak, and as at the moment actually the yen is I think at the lowest level since the 1970s compared to the dollar. So because they argue they want to have a weak yen to boost exports, because Japan is very much an export-driven economy. So all of these things, they matter, and you still can argue that even after doing all of that, it remains a fact that inflation is significant and positive. Yeah, so that would be the next conclusion. Good. Now, the next thing I want to do is I want to really capture the panel data structure. Yeah? Because thus far we ignored the fact that we have actually panel data here. Yeah? That wasn't really captured. We just use a standard OLS, normal ordinary least squares, so we don't tell Stata, hang on, we have here, you know, panel data, so Stata doesn't really use it. Now when you look into the literature, so I go back into this paper, it's discussed as well. I think it's discussed in here, exactly, this is the paragraph. So what most people do is they use a fixed effects approach for the estimation. And they argue to avoid any potential biases arising from correlations between the included variables and the unobserved effects. Now, what does that mean in human language? In human language, it means that a fixed effect, and you have it actually here in the equation, this is the alpha I stands for your cross-section. It means that you put in country-specific effects. So for instance, you would argue that a country has kind of a general long-term growth rate, which might be determined by the country's institutions, the rule of law, the fact that the country has a good infrastructure, and so on, and so on, and so on. Yeah? Maybe also trade relationships, and so on. So these country-specific circumstances at the moment are not captured in our model. Yeah, so a fixed effects model would permit that countries have a long-term growth path that is determined by factors which you might not be able to observe directly. So, for instance, it's very difficult to quantify the quality of institutions. It's difficult. So what you do instead is you simply specify a dummy variable, so simply a 0, 1, for being a certain country. So I would simply indicate whether you are in the UK, in France, or Germany, or whatever. This is then used to capture all these country-specific circumstances. Yeah, so that's the idea of fixed effects. It's actually using a whole set of dummy variables to estimate a country-specific intercept. So that's the idea. Now, how can this be done in Stata? It's very easy. After you specify here your panel data, so we have done the t-set, you simply now do the following. You just put in xtrec and you put here the comma for the option, and then you specify fixed effects option, and I store now in C. So this is all you need to do. So that's running a fixed effects model. So what this does is it basically adds a country-specific intercept into your regression model. It's basically done using a set of dummy variables. So we just run it one more time and see what happens. And now what you see is you get now a more nuanced, I would say, output. It's a little bit more complicated. Now we have to talk about this in a bit more detail. The first thing you notice is we have different types of R squared. Yeah? So before that we had kind of an averaged R squared, yeah, the 21%, but of course we ignored the fact that we have panel data. So now this is of course modified because now we have to deal with 147 groups. Now the groups are actually the different countries. So actually what you do is you increase the number of variables substantially because you have all these dummies, as a matter of fact, in your model. Now the adjusted R squared you see here will adjust for the fact that you have more variables to estimate. Yeah? So your so-called degrees of freedom go down. So what you would look at is the overall R squared. This would be the thing you would use to compare it with your initial model. However, the issue is that the initial model ignored the panel data structure. Yeah? And that's a problem. Yeah? That's not good modeling, so that's actually a specification issue. So you can't say that the original model is better because it has a better R squared. Yeah? I would argue it's most likely biased because you ignore country-specific effects, which you capture in the fixed effects model. Yeah? So within explanatory power is, so inside a country I can explain 19% with all the additional variables. Between means I can compare GDP growth rate between countries and I can explain about 15%. Honestly, for a macroeconomic model, this isn't too bad. It's okay. It's not amazing, but I think it's quite acceptable. In here, we have now further guidelines about our estimation. You see that our coefficient actually goes up a little bit. It's still significant, so still we have to argue inflation has a positive and a significant effect on growth. Yeah, so that's still the case. Now, the lending rate is now a bit more borderline, but still not significant. So if you take the cutoff point for the p-value at 0.05, we are above. So we can't reject the null that this coefficient is equal to 0. Looking at the confidence interval, you see it goes from minus to plus. So that means the 0 is included in this interval. So you can't argue that the lending rate has a positive effect or negative. It has no significant effect. The other effects remain the same. So again, exchange rate is negative. Yeah, so weaker exchange rate is actually positive for growth. Money supply is again positive. A bit, the coefficient is a bit weaker, but otherwise it looks very similar. Yeah. Then you see further an F-test on these fixed effects. So that's a test for all these coefficients, whether they are jointly equal to 0, which you can clearly reject. So this actually tells you clearly that a fixed effects model is a good improvement compared to ignoring this. Yeah. So that's the summary of this output. So after doing a fixed effect specification, we still conclude that inflation has a positive and significant effect on growth rates. Now that's interesting. I won't now go into the difference between random and fixed effects. Again, it would need a separate session to dig deeper into this. I have done actually a video on panel regressions and also compared fixed and random effects, but it needs a bit more ground to cover. And I want to make sure that we are not going way above an hour, just to be efficient in this case. Okay. Good, so the next thing I would like to do is I now want to consider what about nonlinear effects? Yeah, so because that's what the paper we looked at is arguing. So are there any nonlinear relationships? Yeah? So nonlinear effects. Now, the way to do this is we have to predict here our fitted values. I just do this, predict fit. This is basically predicting our fitted values after our regression model. So I just now run this, and we get here our fitted values. So these are fitted values. So basically the idea is what we now do is called the Ramsey reset test. I have done also a video on this. It's basically if you go into omitted variables, you see this test used. It's called the Ramsey reset. And what this test does is it takes my fitted values to the power of 2 or higher powers and then includes these values into my model. Yeah? So what I want to do first is I want to generate now the fitted values to higher powers, and I can do this inside a loop. So I do for values, it's a loop command. I start with 2, I go up to 4. So I go basically from the power of 2 up to the power of 4. You don't need the indentation. We are not in Python, but it's kind of useful. It's easier to read. So I generate here fit underscore, and then in quotation marks, I forgot the index, I. In quotation marks, I put in I. So I starts from 2, it goes to 3, it goes to 4 inside the loop. And that's equal to fit to the power of I. The important thing is in Stata you have to put quotation marks around it. The first quotation mark is below the escape key, the other one is the normal single quotation mark. If you, of course, code in Python, you don't have to. Yeah? You don't do this, you just can use the index I directly. Now this will generate new variables, fit 2, 3 and 4, which are powers of the fitted values. And then the idea of the test is to run the regression one more time and add these fitted values to it. So I do fit 2 and maybe higher values and then see whether they are significant. So that's the idea. I just run this now and see what happens. And what you can see is the fit 2 is not significant. You see that. Yeah? So the p-value is above 0.05. So there is no evidence based on the Ramsey reset test that nonlinear effects really matter. Yeah? Of course, the fitted values would include all the controls. Yeah? So one could argue, why not only do it for inflation? Yeah? So that would be a counter argument, which is a fair argument. So you can also, of course, try this. The other thing, of course, what you could try is to add now more than 1 into it. Yeah? So you can do something like higher orders. Yeah? We can fit 3, for instance. And then, of course, if you want to test that, you have to do now a joint hypothesis test of fit 2, fit 3, if I can spell it. And that would basically go into higher orders, so order 3 and also higher orders. But again, there is no indication. You see this, the F test is clearly indicating there is no indication that this actually works. Now, one counter argument would be, why not inflation alone? Yeah? So you can also argue that maybe do it only for inflation. So that's an argument you can have in your paper. So you would then generate your log inflation 2. And it would be simply your log inflation to the power of 2, and then you would throw this into your model and see what happens. Yeah? So is that adding any power to your model? Yeah? So that's another way to look into this, and in here again you get the same answer. The answer is no, it's not significant. So what we can now conclude based on our initial analysis, now we are exactly after 1 hour, so that's not actually bad. So after our initial analysis we can conclude that inflation most likely has a positive effect, and we don't find evidence that this effect is non-linear. Of course, we have to have in mind we have a data set where we also don't have too many observations over time. So if we do look at the year, we only start from 2004, we go up to 2012, so this is quite a short period. So what if you extend the period, which you can easily do using World Bank data? So that's, of course, maybe a possibility. What if you highlight very extreme levels of inflation? Because we certainly saw that outliers really matter. So there are lots of additional things to explore, but I think for a first, for a first live stream, this I think is more than sufficient. So we covered the basics. The last thing I want to do is now I want to combine all our tables into one table. I can actually do it below here. So I can do an estimates table, ABC. So just to have a nice output table, and then we just run everything one more time. I use stars to indicate significance. I use statistics here. I do the AIC, BIC, and N. So AIC is the archaic criterion. I mispronounce it all the time. BIC is Bayesian information criterion. So these are basically criteria to help us with model specification. I've done a video on this. But basically what we want is we want to minimize these criteria. So they help you for model specification. B specifies that we display coefficients of our models. And now I specify a fixed format, so another %9, and we do .3, so we have 3 decimals. So this should give you a nice table. I'll just run this one more time. Let me just run the whole thing one more time. Now that's the beauty of having a do file. It's all now done for you. It's all updating, so that's pretty good. And in the end, if you go up, you have now here your nice table. Yeah, so that's quite a nice table. You can just simply copy paste that. Again, do a right click, copy as HTML. You go to your Excel. You can start a new sheet and you just copy paste that. You can remove the formatting. And again, you can modify this a little bit. You can move things around so that it looks a bit more decent. And you have a nice table. And of course, again, you can move it now into Word or whatever you want to use for writing. And you can again add some borders here to make it look a bit more decent. But you see how quick that is. Yeah, so it doesn't take you too long to modify tables. Certainly you would never ever start typing your tables again. Yeah? So now you have also your significance levels indicated. It's all looking quite nice and neat. So that's not too bad. The thing to note is when you look at your information criteria, you can't compare your A model with the other ones because your sample size is different. Yeah? And as I talk about this in this recording on model specification, you have to maintain the same sample size to compare your models. But clearly you can see that the AIC is going down and also the BIC is going down in model C. So actually model C would be the preferred model. And that's interesting, well, because model C is your fixed effects model. Yeah? So the fixed effects model would be the better choice for modeling, clearly. Yeah? So that's another indication, apart from the other things we already know. Good, so I will stop here and shut up for a while and just go back to any comments or questions. And of course, again, I will show you in a minute where we have all the details. Good. Are there any further comments or questions? Yeah, so again, this should be available online. in actually most likely less than 10 minutes. It always needs a bit of time to upload. Then you could refer to this again. I want to just show you one more thing. I want to show you, this is the GitHub. So in GitHub you have actually this is me on a good day here. You have all the different parts of analysis which I tend to cover. Honestly, if you focus on a dissertation project, I really like using Stata. It's easy. You don't have to spend so much energy learning something like Python or so, because it's too difficult, to be honest. Spending 4 or 5 weeks learning it just to do some basic stuff. It's not always a good idea. So in here you have all the material. I think personally, the first, I would say 4 or 5 actually the first 4 topics are more than sufficient. So you don't actually need to go that deep. If you have panel data, then go into the panel data analysis part 5. The rest only depends, okay? So binary choice models, so this is logistic models, probability models, this depends on what you want to model. Yes, if you want to model decision making. The other aspects of it are I think also quite useful, in particular on model specification. The last thing which I want to start actually this week is on confirmatory effect analysis and structural equation modeling. I personally think that this is not really needed. Honestly speaking, it's not really needed. Good, so it has been a great pleasure. So I will upload this after the stream. So hopefully it worked and the quality was reasonable. And I see you next time. Again, if you want to see more stuff, you can just drop me a line. You know how to find me. I'm happy to do maybe also one session on Bloomberg or one session on getting data online for free. So that might be useful for some of you. So that's all I wanted to say. So it has been a great pleasure. Thanks for joining, and I see you around. And as always, enjoy the joy of data analysis. Take care. Bye bye. As always, may the power be with you. Take care.